Okay, scholars, today we're going to begin Unit 5, which is all about rotation. Um, we're basically going to take everything that we've done so far, which has been kinematics, dynamics and statics, which is a fancy way of saying forces, energy and work, and momentum. And we're going to apply all of that to rotating objects. Everything that we've done so far has been for objects moving linearly. Now, we have looked at circular motion, haven't we? In our kinematics and our dynamics sections, when we were analyzing forces, we were analyzing objects that were moving with uniform or non-uniform circular motion. So this was things like, an object going around some circular track, going around banked curves, things like that. So those objects are not really moving in a line. Their path is indeed circular, but remember that we approximated them as if every instant in time their velocities were always tangent to the path in which they are moving. So we still kind of consider that to be linear motion. It was one object, a single object, moving in a circular path. What we're going to be doing now with rotation is analyzing objects that are moving in circular paths, but we're going to make it more complicated, and we're going to take our analysis to a different level. A lot of this is going to be kind of familiar to you based on our conversation of circular motion, but like I said, we're going to take it a little bit deeper. So I want us to think about maybe like a spinning record. So let's say that we have a record, and let's say that it's spinning uniformly.
I'm done.
Yeah? Mm-hmm. The hero
fights the monsters with his swords.
Dude, I love it. Great job. Go play, okay?
Can I have some time on the swords?
You can, but I'm not going to be able to help you at all, okay? All right, shut the door. Let's say that this record is spinning at a constant rate. So you know that we could find the center here. We would call this the axis of rotation. The record is rotating about that point. That point is, for all intents and purposes, motionless. And every point along the record is spinning. So if we say a point right there, at any given moment in time, it's going to have some tangential velocity tangent to the circular path. We could look at a point right here, which is also going to have a tangential velocity tangent to its path, et cetera, et cetera. So we could treat this extended object. It is a disk. We could treat it like a collection of point particles, and each point particle is moving in a circle. So circular motion does indeed apply. And let me remind you several different ways that we have of talking about the kinematics of this. So if you wanted to title your notes, we could say this is rotational kinematics. And this should kind of be a review for you guys. So I know that these points have tangential velocities, which I'm going to call VT. VTan, tangential, tangent to the path. And I know that velocity is always equal to change in position over change in time. I'm using an S right here just as a generic variable for position. Instead of saying X or Y, I'm using S because if this was mapped on a Cartesian reference frame, this particle will be changing its X and its Y coordinates. We could and we will talk about how a particle changes its X and Y coordinates when it spins in a circle. That's going to be next unit when we talk about harmonic motion. That will come up a little bit. But for now, let me just say that its position is S. And I'm going to say that S is some arc length, some position around the circle. So let's say that maybe at time 0 when I start my analysis, those objects are kind of lined up with respect to the center right here, and at some time later, let's say that they have displaced over here. So this arc length would be the change in position over change in time, and that would give me the velocity at every instant. Okay, so that's the general definition of tangential velocity. No surprise, change in position, displacement over time. So how do we talk about arc length? Everything that we're about to discuss is going to be completely based around this idea and this equation. You guys must commit this to memory. Imagine that we did actually draw a line connecting all these points to the center, to the axis of rotation. Then we would see, as time goes on, we would see that line shifting. It would be sweeping out different angles. And how is the distance traveled by these particles related to the angle? You guys need to know this. This is the arc length formula. I think it is on your AP equation sheet, but the arc length is related to the angle just by a factor of the radius, where the radius is how far away from the axis of rotation that particle is. So you can see that with the same angle that is swept out here from time 0 to time 1, my particle that is out here at a longer distance from the axis of rotation is sweeping out a longer arc length compared to this particle right here, right? So we've already kind of talked about this. This particle would be experiencing a bigger tangential velocity, wouldn't it? They're both sweeping out the same angle in the same amount of time, but this one has to travel a farther distance. Its arc length is bigger because it is a farther distance away from the axis of rotation. It's going to have a bigger tangential velocity. So it would be convenient for us to kind of redefine all of this in terms of something that is the same for both particles, and that is the angle that is swept out by this line, the angle that they change with respect to the axis of rotation as time goes on. So you know that instead of talking about a linear velocity, we can talk about an angular velocity, which we give the abbreviation omega, the Greek letter omega. Linear velocity is given in units of meters per second. Angular velocity is given in radians per second because it is defined thusly: the time derivative of the angle that's being swept out. So as this record is spinning at a constant rate, it is sweeping out, this imaginary line I've drawn out from my axis of rotation is sweeping out some angle theta in some time interval. D theta dt would then give me angular velocity. So d theta dt is equal to omega, angular velocity. How can we relate these two things? Listen very carefully. This arc length equation up here relates position along a circle to where we are on the circle and how far around the circle we are. In other words, if I wanted to know the position change that this particle sweeps out, I need to know the angle that was swept out and the radius, how far away the particle is from the axis of rotation. So this equation is going to be the equation that gets me from linear quantities to angular quantities. This is a linear position. This is an angular position. So I could rewrite this as this if I'm interested in the change in position. This would be linear displacement. This would be angular displacement. This equation is going to get me between those two things. Well, if I take the derivative of displacement with respect to time, that of course gets me tangential velocity, doesn't it? How far does it go per unit time? What is the delta S over delta t, or ds dt, if I'm talking instantaneously, right? So if I take the time derivatives of both sides of this, I'm going to get this. I'm going to get ds dt, that's the time derivative of the left side. Take the time derivative of the right side, I'll get r d theta dt. Well, what is d theta dt? It's omega, isn't it? So this gives me a way to translate between my two different worlds of linear velocities and angular velocities. You all need to know how to jump back and forth between the two, okay? All right, so where are we? We're talking about two different perspectives we can take for rotating objects. We can take the perspective of worrying about the linear position change per time, the time derivative of change of position. That would give me the tangential velocity. Or I could talk about the angle swept out as time goes on, and that would give me angular velocity, radians per second. How many meters per second is the particle actually traveling? Or how many radians per second is this line on which the particle is located with respect to the axis of rotation? How many radians per second is that line sweeping out? And always multiplying the angular quantity by the radius, where the radius is how far away that particle is, not necessarily the radius of the whole circle, but how far away that particle is from the axis of rotation. Multiplying the angular quantity times that will get me the tangential quantity, okay? Now remember that we said that in order for any particle to be moving in a circle, what must be true about it? It has to have a net center-seeking force, doesn't it? It has to have a centripetal force. So this particle has got to have a center-seeking force, which I've drawn in blue there, a centripetal force. And remember our equation for centripetal or radial force. Centripetal or radial, two different pieces of terminology. It was always mv squared over r, where v squared over r is equal to the tangential acceleration. So I could write this in another way, couldn't I? Excuse me, not tangential acceleration, but radial acceleration, the acceleration pointing inward. Now, the thing is spinning at a constant rate, so d theta dt is constant, v tan for each particle is constant, it's uniform circular motions. So can you explain to me why I'm talking about an acceleration? Right, because every instant the velocity is changing its direction, isn't it? The velocity is always tangential to the path, and there's a direction change there, isn't there? So whenever I have a direction change, that's a velocity change, that's acceleration. That direction change here always points into the middle of the path. Remember, quick review, whenever you have a particle changing directions, there always has to be a component of acceleration pointing into the center of the path, caused by a force pointing into the center of the path. Anyway, another way of talking about radial or centripetal center-seeking acceleration would be just to take this equation and replace v with r omega. So v squared would be r squared omega squared over r, and that of course is going to simplify to omega squared r. So I guess in all this mess there are three big important equations you need to know. This would be how to relate position with angle. So position, angle. You multiply the angle, the angular quantity, by the distance away that particle is from the axis of rotation. Of course, tangential velocity is just what we're used to. And angular velocity is defined as this. How quickly are we sweeping out that angle theta? We call that omega. How many radians per second are we sweeping out? And then to go back and forth from the angular quantity to the tangential linear quantity, of course, just like this, we're going to multiply the angular quantity by the radius. And then you will hopefully remember that even though the velocity, the tangential velocity here is constant, we do have a direction change. So we have an acceleration, a radial acceleration, always pointing into the center of the circular path. We know that's equal to v squared over r, where this is v tan. I can replace v tan with this, and therefore I have a new way of writing about my centripetal acceleration. All of this should be a review for you, I believe. Okay, let's see what happens though whenever we have an object that is spinning maybe at an increasing rate, a non-constant rate. So here's the axis of rotation, and once again, let's say I have two particles right here, and maybe in some time, maybe 1 second, so from t0 to t1, they experience this angle change. So they sweep out some angle theta, and of course they are changing their position, and I could talk about their tangential velocity, which of course would be ds dt, where s is an arc length. But then maybe I just turn my record player on, and so it's speeding up. Well, in the next second, this system is going to be sweeping out an even greater angle. Okay, so in this next time interval, I'm sweeping out an even bigger angle, theta, and my particles are getting faster and faster and faster. They're speeding up. So in other words, this might be the tangential velocity at time 1, but the tangential velocity of this particle at time 2 is going to be much, much bigger. So not only do I have a v-tan, and not only do I have a radial acceleration, of course, please remember that we always have a radial acceleration, whether we're spinning at a constant rate or an increasing rate. If you're spinning at all, if you have an object moving in a circle at all, there's got to be a component of the acceleration pointing in to the middle of the circle. You have got to always have a radial acceleration. So no matter whether an object is rotating at a constant rate or an increasing rate, you will always have these two quantities present. And of course, we will always have angular velocity omega. But now that my rate of spin, my rate of rotation is increasing, not only do I have tangential velocity, radial acceleration, and angular velocity, but now I also have tangential acceleration, which is going to be the derivative of tangential velocity as time goes on. That's no surprise to us. The velocity is not only changing direction, not only do I have centripetal radial acceleration, but I also have tangential acceleration because my velocity is increasing in magnitude. We've talked about this already, that whenever you have an object that is changing its direction and changing its speed, you have to have both of these. Where a tan is responsible for the speed change, so it always points parallel to my velocity. So here is a tan right here. Here is a tan right here. And then of course my radial acceleration would always be pointing into the middle of the path. Okay? So please don't get those confused. The actual acceleration, of course, would be the vector sum of those. All right. So not only do we have a time derivative of tangential velocity, but we're also going to have an angular acceleration. Now listen, radial acceleration and angular acceleration are different. They sound kind of similar. You may get them confused. Please do not. Angular acceleration is the rate of change of angular velocity with respect to time, or the second derivative with respect to angular position. Okay, we give it the Greek letter alpha, and of course it has units radians per second squared. Just like acceleration has units of meters per second squared, radians per second. How many radians are we changing per second, and how are we changing that every second? Please do not get these two confused. Radial acceleration is that center-seeking acceleration from a centripetal force that must always be present when a particle is changing its direction. Angular acceleration only shows up when a particle is changing its speed of rotation, when it's spinning at an increasing or decreasing rate. In other words, when there is a tangential acceleration present. Remember that we said that radial acceleration is v tan squared over r, and because v tan is equal to omega r, we could simplify radial acceleration, that center-seeking acceleration from the centripetal force responsible for direction change. We could simplify that to omega squared r. Alpha here, angular acceleration, is going to be related back to a linear quantity by this. Radius, where the radius is how far away the particle is from the axis of rotation, the radius times the angular quantity, angular acceleration, will equal a tan. So I guess what I'm telling you is that we can go back and forth between radial acceleration, defining that with linear quantities like tangential velocity, and then defining it with angular quantities. And we can do the exact same thing for tangential acceleration and angular acceleration. I'm just begging you not to get angular acceleration, which is the acceleration with respect to the angle that's being swept out, not to get that confused with radial acceleration, which is the acceleration, linearly speaking, that is always present pointing into the center of the path, whether an alpha is present or not. If my angular acceleration is 0, if I don't have an alpha, then the thing is moving at a constant omega. It's sweeping out one constant angle as time goes on. And it has a tangential velocity that's changing direction, so it will still have an angular, it will still have a radial acceleration. Okay, you guys need to understand all of these velocities and accelerations. Tangential velocity and angular velocity, radial acceleration, tangential acceleration, and angular acceleration. Please make sure that you review this until you have this down. And of course, I'll be asking, or I'll be taking questions a little bit later. Let me talk to you real quick about direction conventions. So typically we say that that omega will be greater than 0 if my angle change is greater than 0, defined based on the unit circle. In other words, you all know that in my unit circle, I start with an angle of 0 right here, and my angle gets greater as I go counterclockwise. Same exact thing for all of these angular quantities. If I am rotating counterclockwise, like I am in this example, then we say that my angle change is greater than 0. As time goes on, my angle is getting bigger and bigger and bigger, from 0 to 2 pi. And therefore, my rate of change of that is going to be a positive value. So just follow the unit circle. If you're going counterclockwise, you're going to have a positive omega. If you're going clockwise, then your angle will be decreasing. Based on the unit circle, your angle will be decreasing as time goes on. All right. How about alpha? Well, alpha is going to be positive. Well, let me say this. If rotation is speeding up, then you know that alpha and omega point in the same direction. That's true for linear, right? For linear quantities, that when the velocity and the acceleration linearly have the same sign, positive, positive, or negative, negative, that means speeding up, right? So that's probably the simplest way of figuring out what your sign of alpha should be. If the rotation is slowing down, then your alpha and omega will have opposite signs. They'll be pointing in opposite directions. All right. So that was just a quick note about direction. Let's get some kinematic equations. We're doing kinematics right now rotationally. So just like we have linear kinematic equations, we can get angular or rotational equations as well. So all of this is going to be true only for, of course, these equations are true for constant acceleration. These equations I'm giving you over here will be true for constant alpha. Your alpha may not be constant, in which case you're going to have to use calculus to derive things. So we know that my position equation or displacement is given by delta x equals 1/2 a t squared plus v naught t. What do you think the same equation would be for angular quantities? Well, delta theta is going to equal 1/2 alpha t squared plus omega naught t. It's the exact same, right? What else do we have? We have velocity is equal to at plus v naught. That's just saying that, hey, acceleration is the slope of velocity. Over here, I would get omega equals alpha t plus omega naught. What else do I have? I have v squared equals v naught squared plus 2a delta x. So over here, of course, I'm going to get omega squared equals omega naught squared plus 2 alpha delta theta. And I think those will be our most important ones. Okay, and then remember that to bridge the gap, to convert from linear to rotational quantities, your change in position will always be r times your change in angle, where r is the distance away that particle is from the axis of rotation. Velocity, which is the time derivative of that, is going to be equal to the radius times the time derivative of angle change, which of course is equal to r omega. That would let you get from linear tangential velocity to angular rotational velocity. And then of course tangential acceleration is dv dt, which is just going to be equal to r d omega dt, which is equal to r alpha. So to get from position, to translate from position to angle, you multiply the angle by r. To translate from velocity to angular velocity, you multiply by r. To translate from tangential acceleration to angular acceleration, you multiply by r. All right? Not too bad. I'm going to bring up, to introduce the next concept, let me talk to you real quick about energy. So let's say that, once again, I have a rotating record, and let's say that it's spinning, and I can treat this record as if it is a collection of point particles, okay? I've kind of already done that. So this collection of point particles, of course, they are all spinning with various speeds. And because each point particle here is moving, I can say that they each have kinetic energy. So let me remind you that kinetic energy is equal to 1/2 mv squared. So that's going to be the kinetic energy of each particle. Well, what would the total kinetic energy be of this rotating thing? This is going to be important. We'll talk more about this later, but even though this record is not like moving left or right or up or down, it is still spinning, and that is still considered motion. It still has kinetic energy. It's just a rotational kinetic energy. We'll talk about rotational kinetic energy later, but for now I want to use it to introduce a concept to you, okay? So let's say that the kinetic energy total is just going to be the sum of the kinetic energies of all the little pieces, and that's going to be equal to 1/2 times the sum of the masses of all the little pieces times the square of the velocities of all the little pieces, right? Okay. And then this velocity is going to be a tangential velocity that each piece possesses at every step of the way. So remember that tangential velocity is equal to r times omega. And what's different about these particles is that they all have different radii away from the axis of rotation. So what I can do now is rearrange this equation and plug in r omega right here and say, all right, I'm going to add up 1/2 times the mass of all the little pieces times their individual radii squared times omega squared, but they all have the same omega. So that's going to be a constant. That's not going to depend on what piece I'm looking at. They all have the same omega because remember that they're all sweeping out the same angle in the same time interval. So I can pull that out as a constant. And I'm going to get 1/2 omega squared times the sum of mi ri squared, where this mi is the mass of each little piece, and ri squared is the square of the distance from each little piece to the axis of rotation. So this should look pretty familiar. Kinetic energy is 1/2 mv squared. Right now I have 1/2 this thing times omega squared. So omega, remember, is the rotational or angular velocity. It's squared. Velocity for normal kinetic energy is squared. So this term right here is really important. It ends up being called capital I, and that stands for rotational or angular inertia. Another term for that is moment of inertia. And so if I substitute in an I there, then my equation for the kinetic energy of the rotating object becomes 1/2 I omega squared. It looks just like this equation, but instead of having mass, I have I. Well, remember what mass is in Newton's laws. Mass is a measurement of resistance to motion, which we call inertia. The bigger the mass, the more the object resists its motion. So I is the angular equivalent, the angular analog of inertia. You guys need to know this, I tells you how difficult it is for an object to change its rotational motion. Just like m in Newton's laws kind of tells you how difficult it is for an object to change its linear motion, it's for how difficult it is for an object to accelerate linearly. I is a value that tells us how difficult it is for an object to change its spin, for an object to change its rotational motion. Okay? It serves the same purpose as mass, and it has mass in it, but it's more complicated. Let's look at this equation. So I equals the sum of mi ri squared, where remember what m and r are. M is the mass of each little particle, and r is the distance that particle is away from the axis of rotation. So this kind of makes sense, and you can actually go test this in real life. If you go grab an object that, I don't know, just think about a rod. if you go grab a rod, like a broomstick or something, and you try to start spinning that broomstick, first of all, whenever you spin something, and you guys need to get used to this, whenever we solve rotational problems, the first thing you're wanting to do is define the axis of rotation. What is it spinning with respect to? So let's say that we spin the rod through its center. So the center is staying motionless. You're spinning this end this way, this end this way. And then you change your mind and you start to spin the thing. You start to spin the rod just about an end. Which one do you think will be more difficult to spin? Which one do you think will have a larger I value? Well, let's think about how I is defined. It's the sum of all the masses of all the point particles times the square of the radius, where the radius is how far away they are from the axis of rotation. If I treat this rod like a collection of point particles, let's say like this, something like that, which one's going to be more difficult to spin? Well, this one's going to be more difficult. This one's going to take more energy, more force to start spinning. Why is that? Because it has more mass farther away from its axis of rotation. It has more particles of mass at a larger distance away from the axis of rotation. So its I value will be bigger. This has an I value that is going to be smaller because it has less mass, less far away from the axis of rotation. In other words, if this point particle here is a distance r away from the axis of rotation, then this one is going to be a distance of 2r or something like that. Or maybe to prevent confusion, let me say this whole thing has a length of L. And then this would be L over 2. So this particle here is much closer to the axis of rotation. It's going to make it easier to set in motion. The farther you are away from the axis of rotation, the bigger the I value is. That's how that R term works in that equation. So one way of thinking about this moment of inertia equation is we're not just worried about the mass, but we're worried about how the mass is distributed in that object with respect to the axis of rotation. For things moving in lines, we're just worried about how massive they are. But for things in spinning, rotating systems, we're worried about how massive they are and how that mass is distributed, where it's located with respect to the axis of rotation. All right, so one really big important skill that you guys are going to have this whole unit is knowing how to calculate that I value. For a collection of point particles, it's quite simple. You're just going to sum up the mass of each point particle times the square of its distance away from the axis of rotation. Remember, that's what this R means, distance from axis of rotation. So that's going to be quite simple. What I want to do is talk to you about what happens when it's more complicated, when it is difficult to analyze the object as if it's a collection of point particles. Even these rods that we've been thinking about, it's going to be incredibly difficult for us to pretend like it's just a collection of discrete point particles, 4-point particles, 4-point particles, 8-point particles. That's going to be really hard for us. So what we need to do instead is think about what the object is like as a continuous distribution of mass. And of course, you guys know we're going to use integral calculus for that. So this is the equation when you have a discrete collection of point particles. If you're looking at an extended object, though, like a rod, you're not going to be able to use this. You're going to have to use the more general calculus definition. So basically, we're taking the limit of this as my little piece of mass approaches 0 as I look at infinitesimal pieces of mass all collected together in extended objects. And the equation becomes this, the integral of r squared dm, where dm is my infinitesimal little piece of mass. This equation will work for when you have a rigid object that has shape, like a rod, a hoop, some extended object that you cannot just collapse into a collection of point particles. Okay, kind of looks familiar to us. It's going to end up working a little bit similarly as our center of mass equation did. What was that? The center of mass was something like this, right? Like 1 over big M times the integral of x dm. So remember how we had to solve these problems? We had to relate position and mass. Well, we're going to have to do the exact same thing here, relate position and mass here. And remember that the concept we use to relate position and mass is density. So we're going to have to rely on our old friend density once again to solve these problems. Okay, let me do now. My only goal for the rest of this video is to do some example problems with you. So we want to find the I value. Let me erase this. We want to find the I value for a thin rod about its center. And I should say a uniform thin rod to tell you that the mass is uniformly distributed. Okay, so I always recommend you draw a picture. So here's my thin rod. And we have always, this will be always the first thing you do. Think about where the axis of rotation is. So that's what this is telling you about its center. So here's my axis of rotation. That's always going to be the first thing I define, axis of rotation. I'm going to write my equation, I equals the integral of r squared dm, and now I'm going to think about how I can relate these two things. What I always like to do is draw a little dm piece. So what I'm going to do is I'm going to say, okay, there's a little tiny sliver of mass, an infinitesimal differential dm. And I can see that, why don't I let my axis of rotation be at x equals 0. So I can see that this little dm piece is a distance x away from the axis of rotation. So in order to relate these two things, I need to use density. You guys know that lambda is linear density. Let's say that this rod has a length of L. So total mass over total length will get me this ratio of linear density. Because it's uniform, that's going to be constant. So a little mass over a little L is going to be the same ratio. But a little piece of length is just going to be dx, right? So I can say this, and then I can say that, rearrange that and say that m over L dx equals dm, right? Okay, so now I can rewrite this integral like this. I can say m over L, those are constant, they can come out, times the integral of r squared dx. I've just replaced the dm with m over L dx. And now what I have is quite simple, because r is the distance that the little mass piece is away from the axis of rotation. That's what r represents. And I've already said, hey, I can just represent that with an x coordinate, right? So very simply, then it becomes this. Okay. So what I'm doing is I'm thinking about how each little mass piece is distributed away from the axis of rotation. So the first thing I thought about was what dm is. It's a little piece of mass. It's right there. I had to relate it to position using density. And then I wrote dm in terms of position dx. And I ended up with this integral right here. You should pause and see if this makes sense to you. If you have questions, please write your questions down so we can talk about it. what are my bounds of integration? Well, I'm adding up all these little mass pieces, and you can see that they're going to have a radius, a distance away from the axis of rotation that varies from negative L over 2 to L over 2. So those are going to be my bounds of integration. This is a really simple integral. I'm trusting that everyone here can integrate it. Okay, so there's our final answer, 1/2 ml squared. Excuse me, 1/12 ml squared. Now listen, let me give you a clue about these problems. Your final answer will always be some proportion of ml squared. We haven't talked about this yet, but what units does I have? Rotational inertia, will always have the same units. Mass is in kilograms. Length is in meters, kilograms, meters squared. If you did not end up with those units, if you did not end up with meters, length squared, in some proportion, you did not do it correctly. So that's going to be a hint for you. Any rod, every thin rod that's uniform when its axis of rotation is about its center will have this for its moment of inertia. All right? Let's do another one. Let's do the I for a uniform thin rod. About its end. So here's my rod. And let's say that my axis of rotation now is about the end. Here's my little DM piece. It is located some x distance away from the axis of rotation. My equation is this. So first thing you want to do is draw a picture, locate your differential mass element, and now I need to try to relate that to position. Go to density to do that. Big M over big L. That's going to equal little m over little length piece, and my length is lying along the x-axis, so I can call that dx. So m over L dx equals dm. That's the exact same thing. R here is distance away from the axis of rotation, which will just be an x-coordinate. So I get m over L integral of x squared dx. And this time, it looks like my bounds integration will be from 0 to L, won't they? And we're going to get a different answer this time. So you integrate that. I'll let you guys integrate that. And we're going to get 1/3 ml squared, just like that. Now, let's think about what we've just discovered. I kind of talked about this before, but here's a rod rotating about its center. And here's a rod I want to rotate about its end. There's the axis of rotation. For that one, here's the axis of rotation. Do you remember what the I value was for this? It was like 1/12 ml squared, right? So which one's going to be easier to rotate? Well, this one is. It has a smaller inertia. It has a smaller resistance to changing its rotational motion. 1/12 ml squared. This one up here has a bigger I value. Why is that true? Because I, rotational inertia, has to do with mass and how the mass is distributed, how it's arranged with respect to the axis of rotation. For this orientation, for trying to spin the rod about its end, I have more mass concentrated farther away from the axis of rotation. So of course its I value, its inertia, its rotational inertia is going to be larger. Okay, let's do 2 more. Let's do the I value for a thin uniform hoop, like a hula hoop, about its vertical axis. So here's my hula hoop. and here's my axis of rotation. So I'm going to take a top view real quick of this. And here's the axis of rotation, right? So I want to spin it this way in this drawing, or this way in this drawing, with this being the axis of rotation. So once again, first step, always identify your little dm. So there's my differential mass element dm. And I'm going to write my expression. But this one is really quite simple because all of my dm's are going to be an r distance away from the axis of rotation. If this is a true circle, then every little mass piece is going to be located at a constant r value. In other words, it's unlike the rod. With the rod, my mass pieces were changing with respect to where they were from the axis of rotation. In other words, here's a little infinitesimal mass piece located at some x value. Here's another one located at a bigger x value, bigger x value. So their location arrangement with respect to the axis of rotation was changing. Here, though, this r is constant. The distance away that each little mass piece is from the axis of rotation is constant. So I can just rewrite this like this. And guess what, my friends? That r squared is constant. It comes out of the integral. What's the integral of dm? It's m, it's mass. So this is very simple. It is the mass times the radius squared. That will be true always for a thin hoop. Yay. All right. I think I said 2 more earlier, but I lied to you. Let's do 2 more from this point. This time, instead of having a thin hoop, we want to find the I value for a thin solid disk, thin solid uniform disk about its vertical axis. So here is my disk. Oh boy. And here is the vertical axis of rotation, just like that. Once again, let me draw a top view. Here's the axis of rotation. So this is a little bit more complicated because this is not a hoop. This is actually solid. All of this is mass in here, right? This is all mass. So one of the first things you want to do is identify your little dm, your infinitesimal mass piece. And we can't just say it's like a dot because that would be crazy. I'd have dots everywhere and that would be difficult to integrate. So what I'm going to do is treat this disk as if it is a collection of rings, as if it's a collection of hoops. And I'm going to let this be my dm. All right? So right away I'm thinking I'm going to have to relate mass to position. Position away from the axis of rotation. So I'm going to need to use density to do that. And this is a solid flat object. So this should be like really thin. I drew that too thick, but it's a thin disk. So for a solid flat disk like this, I'm going to have to invoke the principle or the idea of sigma, which is surface density. That's mass per area. Well, what is the big area of this thing? It's pi big R squared, where big R is the total radius, right? And that's going to be true for little mass times little area, okay? So you have 2 options for defining that little area right now. One, you can literally just take the derivative of area, in which case you'll get sigma equals m over pi big R squared. Zoomed in perspective, remember we always want to take a zoomed out perspective for the whole object, zoomed in perspective for our little infinitesimal mass piece. The derivative of area is just 2 pi r dr, where of course my pieces are going to have different little r radii. Another way of thinking about this is just to look at the drawing. This ring right here is I can treat it like a little hoop whose circumference is going to be 2 pi r and whose width is dr, some little tiny piece of that radius. In other words, if I were to cut this and unfold it, it would have a length of 2 pi r, that's the circumference of the circle, and a width of dr. And how do you find the area of something? Length times width, right? So 2 pi r dr, that's another way of thinking about it. However you want to define and write an expression for that little area piece is perfectly fine. So I rearrange this and I get that m over pi r squared, big R, the total radius of the thing, times 2 pi little r dr equals dm. And now I'm ready to actually do my integral. I equals the integral of r squared dm. Well, I've just said that all this crap equals dm, so I can pull out all my constants. I can see that my pi is going to cancel out, pull the 2 out, r squared, the integral of r times r squared, this gets me r cubed dr. And I'm going to integrate this. I have all these little rings whose radii are going to change from a radius of 0 to a radius of big R. So I'm going to integrate this from 0 to big R. And this is a simple integral that now everyone should be able to do. You do that and you're ultimately going to get the answer of very simple 1/2 m big R squared, just like that. If we compare that to our answer for the hoop, the hoop had an I value of mr squared. The disk now has an I value of 1/2 that. So this tells me that the disk is actually, it has a smaller inertia, it has a smaller rotational inertia. It would be easier to change the rotational motion of the disk than the hoop. Why is that? Because the disk has more mass located toward the center, toward the axis of rotation. It's got more mass in here than the hoop does. The hoop just has mass out here, very far away from the axis of rotation. So it makes sense that the disk would have an I value that is less. So you guys should not only be able to calculate these I values using the calculus, but you should also be able to understand what they mean and why they make sense. Remember, I is rotational inertia. It is just like normal inertia in the sense of its conceptual meaning. Linear inertia is how difficult it is for an object based on its mass to change its motion, how much force is required to change an object's motion. Here, the I value, rotational inertia or moment of inertia, is that same idea, just rotationally. How difficult is it for an object to change its rotational motion? How much does an object resist changing its rotational motion? The bigger the I value, the more inertia, the more difficult it is to change the object's rotational motion. It depends not only on mass, but on how that mass is distributed with respect to the axis of rotation, because this r here is the distance from the axis of rotation. Okay? All right. Let's do one more. Okay, this one is really complicated, and I do not think it will show up on your AP exam, but it's good to be able to do these expressions. We want to find an I for a uniform, a spherical shell. So here's my about, I always have to define the axis of rotation, right? About its middle. Okay, so here is my, oh boy, here is my sphere. So remember that I always want to first try to figure out what my little dm pieces are going to be. So I'm going to let my dm piece be a little strip of the shell. So basically like a little hoop, a little ring. Just like that. So you can imagine I'm just defining a little segment of this ring, of this shell. right there. So I'm going to let that be my dm piece. Okay? So the first thing I want to do is think about how I'm going to relate things to the axis of rotation. So it's a uniform hollow sphere, it's a shell, so all it has is surface area. So I'm going to use sigma, which is the ratio of mass to area. And of course, the surface area of a sphere is 4 pi r squared. And that ratio will be the same for my little mass. So what is the area of my little mass piece right now? So remember, I can treat this like it's a strip, a strip of paper or something. I can cut that, lay it out. Well, it of course is going to have a length of the circumference. I'm going to let this right here be little r, where little r is the radius of that little strip. And I'm going to say that this width right here is dr, some little tiny piece of r. So therefore, its area is going to be length times width. Its length would be 2 pi little r, and its width would be dr. Okay? Now, this is the trickiest part of this whole thing. I'm ultimately going to okay, so this is the trickiest part of the whole thing. I need to rewrite dr and rewrite this bottom piece because I recognize that dr has another meaning. To show this meaning, I'm going to draw over here because I'm running out of room. So I'm going to draw another little strip over here. And what I can recognize is that from the very middle of this thing, I could draw a line out to that strip, and that would have a length of big R, the radius big R. And I can recognize that if I were to shift that line over just a little bit, I would end up sweeping out an arc length whose thickness is dr. So in other words, if I were to shift my r, if I were to shift this line right here just a little bit, then it's going to end up subtending that dr piece, and that's going to be an arc length. And I know that arc length is always radius times theta, but I haven't really moved a big angle theta. This is like a little tiny angle d theta. So what I'm saying is that this dr right here can also be thought of as an arc length, r theta, where really I've moved some tiny little angle theta, so r d theta. So I can replace dr down here with r d theta, so 2 pi r times big R d theta. But now my problem is that I have two variables that I'm trying to integrate. I have r and I have theta. How can I relate them to each other? Well, what I can recognize, and I'm going to do this over here, is that here I have r, and this was the radius little r, which is the radius of each little strip that I'm trying to integrate across the whole thing. And what I can recognize is that I can write an expression between theta and little r, can't I? I know that the sine of theta is equal to little r over big R right here. I have a right triangle. And therefore little r is equal to r sine theta. And I can plug that in here. So finally I'm going to get that big M over 4 pi big R squared, which is sigma, is equal to dm over 2 pi, little r is now big R sine theta. I have another big R d theta. Rearrange all of this and try to simplify it, and rearrange all this and try to simplify it, and I'm going to get that dm equals 2 pi r squared sine theta d theta over 4 pi r squared. You can see that my r squareds cancel out, my pi's cancel out, this will cancel out to 1/2. Oh, and I left out an m, didn't I, when I bring that up? So I need an m here. So that's going to equal m sine theta over 2 d theta. That's what dm is. And so now I can start to do my actual integral. I is equal to the integral of r squared dm. And I've just said that dm is equal to this. So I is equal to r squared times m sine theta over 2 d theta. I still have this little r in here, but I've already said that little r is big R sine theta. So my I is going to be equal to, I'm going to pull the mass out, pull the 2 out. I'm squaring little r. So I get big M r squared. I square little r, so I get an r squared from this, over 2 times the integral of sine squared theta times sine theta d theta. I get sine squared theta because I'm squaring that little r. Little r has sine theta in it, and I already had a sine theta outside right there. And now what I can do is use a trig property. Oh, and what are my bounds of integration? Well, think about this theta. I'm gonna, in order to get the whole sphere, I need to sweep it out from an angle of 0 to an angle of pi. So my bounds will be 0 to pi. Sine squared theta can also be written as 1 minus cosine squared theta. So I can rewrite this whole thing as I equals big M r squared over 2, the integral from 0 to pi of 1 minus cosine squared theta times sine theta d theta. The idea of doing that is that now I can use u substitution. If I let u be cosine of theta, and du, I have a du, don't I? Du is negative sine theta d theta, or I can say that negative du is sine theta d theta, which means I need to bring a negative sign out. But now you can integrate this, and this should be not too bad of an integral for you to perform. I'm going to leave it up to you. But the main ideas you should be getting, and again, this is a quite complicated problem that I don't think they would pull on you for the AP exam, but the problem-solving strategy is the same. I have got to first identify my little dm piece, and then I need to use density to relate that mass to position. So here I'm relating mass to area, big mass to big surface area of the sphere. 4 pi r squared is the surface area of a sphere. And that's going to be equal to a zoomed in perspective, little mass times the area of this strip right here. Well, it's going to have a length of 2 pi r, because that's the circumference, a width of dr. And then I just said, well, what if I view this in terms of angles, and I let my dr be a little arc length that's swept out by some little tiny change in theta, d theta. So from here, moving this r, this radius, until I get to the end of that dr. So dr, the arc length there, is radius times the angle that I've swept out, where it's some little angle theta. And then I recognized I had 2 different variables, so I need to put them in terms of each other. But I said, wait a second, this little r is the leg of a right triangle whose hypotenuse is big R, and which angle down here I can just call theta. So the sine of that angle is little r over big R. Rearrange this, solve for little r, plug it in here. I rearranged, and I got my dm ultimately to be this. Plug that in here, and then I recognized I still had an r squared in my integral. I've already defined what r is, so square those, and then finally I got this. I had to use a trig identity to say that sine squared is 1 minus cosine squared. The motivation for that was so that I could use u substitution u is cosine, and du is negative sine, and now you can integrate that. I'll leave that as an exercise to you, but whenever you do that, you end up getting 2/3 mr squared, which is just what we want because remember, it's always going to be some fraction times mr squared. Okay, you guys are going to practice this a lot. I'll be able to answer questions for you. So thanks for watching.